Hello, my name is Ben Wright. I teach at the University of Chicago, and what I want to talk about today is measurement. We are so used to the measures, so accustomed to the measures that we use in everyday life, the measures of weight and height, temperature, pounds, inches, and degrees, that sometimes we forget how hard it was for us to construct those measures in the first place. Nowadays, we take them for granted, but in the history of science, we can see how difficult it was for scientists, our ancestors, to create these variables. The variables didn't occur by themselves, but instead were invented by ingenious experimenters who constructed equipment, agents, instruments, which produced the information, produced observations which contained the information which we now call measures. The reason I mention that is because there is a great desire for variables to measure our psychological world, for variables of competence and ability and interest and attitude and mood and morale. And there has been a great struggle for at least a century to construct variables of this kind, some of it more successful than others of it, other parts of it. But the job is not as hard as it might seem, providing we keep our eye fixed on the intention and pursue that intention with determination and with discipline. And what I want to talk about is how it's possible to use the basic idea of measurement as a guide to construct psychological variables. Now what I want to do is to talk about the basic idea of measurement. And we can represent that idea by drawing a line on our chart here, which has a direction and goes from less to more. The line represents our idea of the variable. It can be marked off in equal distances, which represent our idea of units in which we're going to measure the variable. Now, this line has to have a definition, an operational definition, a definition of content and substance. For this, we have to have some instruments of measurement, some questions or probes which we place against the person, and in their reaction to which we see how much of the amount we're after they actually appear to contain. So in going from what we want to know to what we can actually observe or experience, we have to bring in another element. What happens when this person answers this question, when this person tries out this item, when this person confronts this challenge to his competence, ability, or interest, this opportunity to express himself? In the simplest representation of what we can observe, we can define an event. When it occurs, it means the person is showing a sign of the attitude or competence or interest we are seeking. When it does not occur, we can say it does not show a sign, and we can represent that occurrence or non-occurrence by a 1 if it occurs and a 0 if it doesn't occur. So that X is our observation, but only as a means to find out about how much the person has of what X is a sign of, where X is provoked by an item, a question, a challenge, which contains in its definition, in its content, the name of the variable we are after. Suppose that the item is an arithmetic question, and the event is to succeed in solving it correctly. The item is asking about arithmetic. The observation is, does the person solve the problem or not? If he solves the problem, that's a sign of arithmetic ability. If he does not solve it, it's a sign of absence of arithmetic ability. And our aim is to construct enough items of the same kind to produce enough observations of a particular person's arithmetic behavior so that we can count how many of those problems he gets right and use that count of successes as an indication of how much arithmetic ability the person has. Now, I've chosen arithmetic because it's an easy one, but this could be a preference for some product, or an attitude towards, or preference for some candidate. It could be an attitude towards an activity or a possibility or a school or a nation. And what we could be asking is whether they are for it or against it. So that the probe that comes through the item is quite general. It can be any topic that we're interested in, any psychological topic, any topic which bears on interests or attitudes or preferences or abilities or competence. And each time, the important thing is that each question we ask is about the same thing, but another question on that topic, and that we observe how the person responds, counting whether they respond in a successful or more mode, or whether they respond in a less successful or less mode. Now, what we want to know, what we can observe. How are we going to get from being able to observe X's, that is, responses of people to items, to measures of the people on a variable, on a line, defined by the items? That's the objective. That's the idea of constructing measurement. Now I'm going to turn this over, and I'm reminding us up here of the situation. We want to know B, the measure of the person. In order to know the measure of the person, we need to find out D, the calibration of the item. But all we can observe is what happens when the person takes the item, when he answers the item, when he rises to the challenge. Furthermore, we know that the way things happen in real life, even if you ask a person an easy question and they ordinarily have a competence or an ability far above it, they may sometimes get it wrong. And also, if we ask a very hard question for a person, one that they ordinarily would not succeed on, they may sometimes get it right. So we cannot have a simple one-to-one relationship between these answers and how much the person possesses of the variable and how difficult the question is with respect to the variable. We must go to some kind of probability condition, some kind of chance. We must ask the question, what is the chance that this person will answer this item correctly? Or what is the chance that this person will subscribe to this proposition favorably? Or what is the chance that this person will agree with this condition favorably? Therefore, we need some kind of formulation. We have to use what we can observe, X, to infer what we want to know, B and D. And for this, we have to construct a simple relationship between the chances of X occurring and the amount the person has and the amount the item has. Now, here is the simplest possible relationship for these two to follow, which meets all of our requirements. In the red box here is the basic model by which measures are constructed. The model is completely abstract. It specifies the kind of relationship we want to have between the measures we're going to infer and the calibrations from which we're going to infer them, and the experiences we can observe, the events we can observe, the agreements with the proposition, the successes on the item we're going to observe when we give items or ask questions of persons. This relationship contains a logarithm. These are the odds for a right answer or an agreement. This is the log of those odds, or a logit, so-called, log odds unit. And these are in logits. But if we want to solve this equation for the chance of an agreement, the chance of a right answer, we then have to decide what base this log is in and do the algebraic rearrangement necessary to solve for the chance of a right answer. It is customary to use the natural base for this log, so these are sometimes called natural logarithms. And when we use that and solve for the chance of a right answer, we get the following expression. The chance of a right answer equals the exponential function of the difference b minus d divided by 1 plus the exponential function of the difference between b minus d. The exponential function is a way of writing a certain number e to this exponent, but instead of having to write it on 2 lines, we write it just on 1 line. That's a standard practice. If it's not familiar to you, I wouldn't fret about it, but the number is 2.7 and some more, and this is the exponent of that number, and this is just a straight algebraic solution to this proposition solving for this term in this equation. Now, this form is useful to us, and I'll tell you why. This is the chance of a right answer, and here is the related chance of a wrong answer. And notice that this plus this, when they're divided by this, add up to 1, because we are setting up a situation where only 2 things can happen as far as we're concerned. Either he agrees or he doesn't agree. He succeeds or he doesn't succeed. And so the form of this expression is always one in which the denominator, the thing dividing, is the sum of the possible numerators. And there are 2 numerators possible here Here they are summed in the denominator. Now, why is this useful to us? Because we are now going to observe some x's. We're going to ask some questions of some people. And when we come to apply this formula, this model, to take our observations and turn them into estimated measures and estimated calibrations, we're going to want to try to make the observations x as close to their probability, to their expectation as possible. And for that reason, this form of the model can be put to work. And here is the way it can work. There's the form of the model repeated up here. Here it is put against the observation. And this difference is the thing we want to make as small as possible. And one way we can supervise the magnitude of this difference is to square it, to divide it by a scaling factor which standardizes it, and look at these z-squares, which are squared standard residuals. And the study of these squared standard residuals, we get one for each person on each item they take. We get one for each item for each person that takes it. The study of this allows us to direct the improvement of our measure. If these are too big, we may decide we can't construct a measure from the data the way we have it. We may have to make more careful observations, ask better questions, give the people answering the questions better instruction on how we want the questions answered. But in any case, this is the guiding line which helps us to construct our variable. The smaller we can make these differences, the better we are doing. And so it isn't only a question of having a recipe, a formula for turning observations into measures and calibrations, but we must also have a guiding indicator which will tell us how well we're doing and guide us to improve the construction of the measurement in the direction of ever better items and ever better measures derived from them. That's the end of my mathematical introduction to the basic idea that enables us to construct measures. Now, if you're interested in pursuing these ideas further, there are places you can go. There is a book by my teacher and friend George Rasch, put out by the University of Chicago Press, which you can obtain. Here's the book. It's a book that was written in the 50s by George Rasch, a Danish mathematician who worked with Ronald Fisher in the 30s, the English statistician. And it's the book which introduces the idea I've just outlined and shows how effective it can be in the construction of measurement. Then later on, I and my students have written 2 other books which work out problems of this kind in detail and show examples. One is this book called Best Test Design, which is available from the Mesa Press in Chicago or from Mediax in Westport. And the other is Rating Scale Analysis. It has the same sources. The difference between these 2 books is that the red book talks about observations that are simple dichotomies, yes, no, right, wrong, agree, disagree. However, the same idea can be put to work to look at rating scales and partial credit observations. So this book deals with that problem. It shows how you can use the basic dichotomous model, the model for a yes-no event, to deal with rating scales and counts of events and items that have been, I don't want to forget it. It shows how you can generalize the simple model to more complicated observational formats. Okay? It's nice to have a good idea about how to construct measures, but it's better to be able to put the good idea to work. So what I'm going to do now is to go through the results produced by a computer program called Microscale, which applies the Rasch model for measurement to some data. In this case, the data is liking for science data. And what happened was that 70 or 80 children were asked how they felt about a variety of activities which contained some scientific content. And they were able to respond by drawing a smile in the face, leaving the face more or less blank or non-committal, or drawing a frown. In other words, they were asked to say whether they liked the activity, a smile, didn't care one way or the other, a non-committal face, or disliked the activity, frown. The kinds of activities offered were go to a picnic, go to a museum, study birds, study plants, look things up in an encyclopedia. The full details of the items can be seen in rating scale analysis, where this example is discussed in detail, or in the manual for Microscale, which is in this binder. In order to understand how the program works, however, we don't need to get into all the details right now. So instead, let's look at the first view that the program produces for us of the way the data looks after it finishes analyzing them. So now we need to see on the screen the first view, and here it is, liking for science, children, activities. Now we can change these labels. In this case, our subjects were children, so we call them children. And our questions were activities, so we call them activities. And the opportunity to respond was in one of three categories, a frown, a non-committal, or a smile. So there are two steps involved, the step from going from a frown to a non-committal face, and the step from going from a non-committal face to a smile. On top of the line, the program Microscale has told us where the children are positioned on this variable. Here is the least favorable attitude towards science, or least liking for science. Here is the most liking for science. Here are a couple children here who, by their smiling at almost all of the activities, are saying they really like science. And here are a few children down here, by the frowns that they are putting by many of the activities, are saying that they don't like science very much. And we have each child positioned along this variable, and we've counted how many children actually fell at each point. That's what this vertical line up here is. So we can see we have the variable, we have the children measured on it, we know who likes science, who doesn't like science, and we know how many children there are at each position. At the same time, this line would have no meaning if we could not explain its content by knowing where the activities through which the children tell us how much they like science are positioned. So here we have, in the purple lines, the position of each activity with respect to going from a frown to a non-committal. So this is the position of going from disliking the item to not disliking it. Then we have the second step in the response format, namely going from a non-committal to a smile. That is, from not saying you like it to saying you do like it. So we have again the same items positioned with these white lines. So you can see here there are several items here going from a frown to a non-committal, and those same items going from a non-committal to a smile. So we learned then that here we have items that they're very easy to not to frown at, like a picnic is very easy not to frown at. Here we have an item that's very hard to like. It has to do with studying rats or collecting old bottles and cans to see what's in them. So the activities themselves have defined a variable from which has substantive explanation from not liking science to liking science, and the persons have been measured along that variable. Let's look now at a diagram of what was on the screen. We call this a map. The distribution of the persons on the map gives us the norms for the variable. As we see how many people there are who have less of the variable and how many people have more, we get a picture of how these kinds of persons are distributed on this variable. If we want to do any normative referencing, we can use this distribution of people to establish our norms. Notice here there are a few people in blue who really have very little of this variable, and they stand as outliers. Then here is the bulk of the people spread out about here on the variable. There isn't anybody up here in this sample of people. At the same time, this line has a definition in terms of the items which define it. This is what gives the line meaning and helps us to explain what it means to be where these people are. Down here, the items provide a criterion or substantive definition of the variable. If we were doing criterion reference norms, we would look on this side of the line to see what is it that a person like this knows? What is it that they've mastered? If these were arithmetic items, and this we would have arithmetic ability here, and we could say of this person that he had mastered these items below him, but he had not yet even begun to master, say, these items way up here, and he was just beginning to be able to deal with these items. On the other hand, a person up here is way past mastering these items and is really at grips with these items up here. So we can use, not only do we get the criterion referencing or the operational definition of the variable below the line and the normative referencing of the variable above the line, but for any person that we're interested in or any position that we are interested in, we can talk about what that position implies with respect to mastery and readiness and much too hard still. So if we take that position, we see there's a region below them where we have maybe practice, and then here mastery, and here readiness, and here still to be gotten ready for, much too hard to start with. So that the distance along this line has an interpretive meaning which brings together where the person is and what the items tell about the variable. The items define the variable. Their calibrations tell us where what is. And then the people are measured on the variable, and we see there where who is. Okay, the map we just looked at is, of course, just what we want. But we have to stop on our way and ask how good the map is. And by that I mean we have to ask how well do the answers that the children gave to the questions, in the case of liking for science, for example, how well do they fit together to support such a map? And for this we look into the fit statistics. That is the analysis of the difference between what the children did and what our summary of their behavior says they're supposed to have done. And the first picture of that is here. It's view 2 in microscale. Here we have the activities positioned and how easy they are, from easy to like to hard to like. And here we have a new statistic called the outfit. And what it is a statistic which pays attention to how far the actual behavior of the children is from what we expect it to be. And we see that for 2, maybe 3 of the hard items, we are getting an indication that those items have some unexpected or misfitting responses to them. Where we would like these points to cluster is along the 0 line. As long as they cluster along here, we know everything is okay. When they go away from this line up, that tells us that something unexpected is happening. There's some noise, some irregular, inconsistent behavior on the part of some children with respect to these particular items. These are also the hardest to like items, and in this particular case the interpretation becomes that these items were straining so, in the composition of these items strained to find something really hard to like that was scientific. But unfortunately in this composition the items strayed from liking for science and became a bit obscure. And for that reason, there were some children, will turn out when you analyze the data carefully, it turns out that there are some children who, even though they didn't like science very much, they liked these activities. So they were partly spoiled as representations of what the rest of the activities get together to measure. This is a very important view because it tells us the extent of our success in defining a liking for science variable, and the places in our data in terms of particular activities where we have trouble and where we might still be able to improve the construction of this variable. Let's now look at the next view. This is the third view. You remember the first view was the map, which showed the relationship between the persons and the activities, and the second view had the name outfit over here, and the activities spread out according to their difficulties. Now, infit is another way of looking at the discrepancy between what we observe and what we want to observe given our intention to build a variable. And we see that infit also implicates the 2 most difficult items as containing irregular response behavior in them. The third item, on the other hand, doesn't show up as quite as badly on the infit view as it did on the outfit view. Now, what has happened here? That's the question that you would be asking yourself. We have 2 different fit statistics. They are closely related to each other, but they put emphasis in a different place. This third item, which looked bad on the outfit graph does not show up on the infit graph. And so this raises the question, what's the difference between these two fit statistics? To see that, we'll need to look at a new graph, the next view the program provides, which plots the two fit statistics against each other. Here we come to the next view. You see outfit is there and infit is there, and there are the liking for science activities. And there are those two that stood out in both the outfit graph and the infit graph as containing irregularities. And here is the third one. It was also the third most difficult, and it is not quite as bad on infit as it is on outfit, but it still is distinctive. So we see from this report on what's happened when we tried to get calibrations for the activities and measures for the children, what has happened, and that is that two items have not cooperated, but the rest of the items, focusing around the reference point of 0, 0 here, which is where we're aiming at, the rest of the items have cooperated in helping us build a liking for science variable made out of activities which a child may express their liking for. Now, when you start to study these data, or in the case of your own data, you will be interested in which items fall in this region of the outfit-infit plot. You might still be wondering why we're bothering with an infit and an outfit, since, as you can see here, they tell very much the same story. And that's true. They come from the same discrepancies between the observation and its expectation. The only difference is that this one emphasizes the outliers, the extreme items, the items which are far away from the children. Whereas this version of the relationship between what we observe and what we expect or what we hope for emphasizes the inliers and the relationships between children and activities which provide the most information. So the mnemonics here are infit for inline fit and information-weighted fit, and outfit for outlier fit, and that's as far as that mnemonic goes. And they give very similar information, but in the case of this item, there is more outlier misfit than there is inlier or information-weighted misfit. We have just been looking at what happened when we tried to use the 25 activities as a basis for defining a liking for science variable. And we found out that all but 2 of the items worked quite well to serve that purpose. Now we want to look at the children and see how they cooperated with this variable that we are constructing. And this is a plot, the next view is a plot of the children, from the children who like science the least to those who like it the most. And here we have again the outfit or outlier sensitive fit statistic. And here we see that the children who have moderate liking for science, they fit quite well. Their points are near the 0 line in outfit. But that there are a few children here and here who don't cooperate in a consistent way with the opportunity to express their attitude towards science with these activities. These children who don't like science very much because they're at this side of the view, of the plot, also have a few irregular responses. What that means is that they have liked some activities which are hard to like in general, while not liking other activities which are easy to like. They don't like many activities or they wouldn't be down here. But they must have chosen a few activities to like which are unusually hard for most other children to like, or they wouldn't be up here. And so we see we have about 5 children, maybe 6 or 7, of the 75 involved, for whom a good measure was not obtained because they did not use the activities in the same way as the other children. We're going to now go to the infit view of the same data and see how it looks. Here again are our 75 children, positioned horizontally by how much they like science, and vertically by how consistent their string of responses is with the definition of the variable. And again we see that there are 2 children here who they don't hate science, but they're on the low end of the liking for science variable, and they are showing quite a lot of misfit here. This is the information weighted, or the inlier misfit, so it means that the center of their response pattern, that is their behavior with the items which should be most suitable for them to use to express their liking for science, is inconsistent. There were, in the outfit chart, we saw about 7 children here. Now there are only 2. What this tells us is that there are 2 who have a really bad pattern, a really inconsistent pattern as far as our intentions are concerned, namely to measure the children on a single liking for science variable. Let's now go to the next view. Here is the third children's view. We had outfit against liking for science and infit against liking for science, and now we have outfit against infit. Again, we see that they tell very similar information. We also see that most of the children's behavior is consistent with our construction of a liking for science variable. That is, it focuses around the center point of this plot, the 0, 0 point. We also see that there are these 2 children who are bad on outfit and bad on infit. Their response patterns are definitely irregular or anomalous, inconsistent with the variable that we have constructed here. We can't take their scores on this test seriously. We must find out what it means that they have behaved in the strange way which is earmarked or indicated by their position in this plot. Over here we have some other children whose infit is not so bad, but whose outfit has become a bit extreme. What does that mean for these 5 children right here? It means that in general, in the center of their response, in the center of their behavior, things are almost okay, but that there are a few outline, a few irregular responses where they have liked an activity which is very strange for them to like because it's so far from them in its calibration, or they have disliked an activity which is strange for them to dislike because it's so far from their calibration. To find out exactly what this means about those children, we have to look at their particular response patterns, at their particular string of responses, and see on exactly which items they express their irregular behavior. After we look at that, we can then decide what to do about the measures of these children. Nevertheless, we see that for 65 to 70 of the children we measured, out of the 75 total, we got a good and useful measure, and this picture is our verification of the quality or validity of our measures. Let's go to the next view now. Isn't that pretty? All right. This is the final standard view that Microscale provides, and it gives you a picture of how the 3 response categories worked with these children. This purple line here of squares is the probability of frowning at an item, which is set for this, is set the same. The pattern of this probability is the same for all the children and all the items. It's the difficulty curve or the chance curve for marking down a frown. If the child is way over here, very much disliking an activity, that is, this -5 says that the child's level of liking for science is 5 logits below the demand of that item to be liked. So this means this child, right here we have a child confronting an item that he really doesn't like, and his probability of frowning is very high. But as the distance the child's liking for science is below the item difficulty moves up, the probability of a frown drops and drops and drops until it becomes virtually 0 when the child is much more fond of science than the item demands to get a smile. So here we have the declining probability of a smile. Over here we have of a frown, excuse me, the declining probability of a frown. Here in the blue triangular line we have the rising probability of a smile. Child down here is not very likely to smile, but as he moves past the item and he likes science a lot and it's an easy item to like, then he will almost certainly smile at it. So here we have a picture of his chance of smiling. In between is the chance that he will neither frown nor smile, but leave the face blank and non-committal. We can see that when he's in an intermediate state, he's not necessarily likes science more than that item requires or less. He is most apt not to mark it either a smile or a frown, but just to leave it blank or put a straight line for its mouth. This makes sense, of course, because the probability of an intermediate response must come in between the probability of a rejection and of an acceptance. This view gives you a picture of how your response form is working. In this case, the response form is the opportunity to frown, to be non-committal, and to smile. Here's the curve for the frown. Here's the curve for the non-committal. Here's the place at which the probability of not frowning drops below the probability of being non-committal. Here's the point where the probability of smiling gets higher than here's the point the smiling is higher than frowning. Here's the point where it's higher than being non-committal. And from here on, a smile is the most likely response, becoming more and more probable as the person likes science more and more, or as the item gets easier and easier to like. I've enjoyed talking with you about measurement. I've done it in three ways. I began by talking about the measures we're used to, such as inches, pounds, and degrees. And then I went to the basic idea which lies behind those kinds of measures and which can also be used as the basis for constructing psychological measures. Finally, I showed you some views that come from a computer program called Microscale, which makes it easy for you to actually apply these ideas to your own data. In some ways, the proceedings may seem abstruse to you because I was only able to touch on the leading features. And of course, we both recognize that to master the details, you will want to study various books on the subject. But the real proof of the pudding will come for you when you apply these ideas to your own data. There is nothing more convincing than that, and you can become convinced of the usefulness of a program like Microscale even before you master the details of its construction or the mathematical basis on which it's built. The most useful thing you can do for yourself is to take some data where you have tried to define a variable by writing questions which go together to pursue a particular line of inquiry, and where you have given these questions to persons for whom you believe they were suitable in an effort to find out how much of this variable those persons had. Any questionnaire or test where you planned to compute a single total score at the end, a count of how many agreements or how many right answers, or how far in the rating scale format your respondents actually placed themselves. Any questionnaire of that kind can be analyzed by a program like Microscale. If you use Microscale, if you take data of that kind and enter it into your computer and apply Microscale to it, you will find out then whether this is useful to you, because Microscale will tell you how much each person has of your intended variable, how difficult each of your questions is with respect to your intended variable. In its first view, it will show you where the people are and where the questions are. Then in its next three views, it will tell you how well your questions actually worked in doing this. If they worked well, it will show you that. If they didn't, it will tell you which questions didn't work well, and then you can examine those questions and the persons with whom they didn't work well and decide for yourself if this is a useful thing for you to do. The next three views will tell you the same kind of information about the persons. For whom did the measure work well, and how well did it work for them? Finally, if you're interested in the response form that you designed, if you have a rating scale with 4 categories or a questionnaire with 5 or 6 categories of response, you will be interested in how those alternative opportunities to respond have actually functioned with your people. And the last view will give you a picture of that functioning. And then in the tabular output from Microscale, you will be able to see actual numerical values for fit statistics, which will tell you, which will advise you as to which aspects of your response format were working well and which were not. So while I hope you will study the topic, what I urge you to do is to try out the program, because no matter how much you study the topic, you won't believe it's useful for you until you see it working on your data in a way that you yourself find useful. Thank you very much.